Two very important terms. Coupling, the first one. Coupling is basically how different entities in your system, your classes, then in a higher scale, your modules and packages, your components, components of your software system, how dependent to each other they are. Down below you see two figures. On the left, we have tight coupling, and it means your software or your modules are more interdependent, they have more coordination, and they have more information flow. On the right, we have loose coupling. So each of the components associate only with the neighboring components, while in tight coupling, components associate with every other component. This is, for example, an example of very tight coupling, that each module depends to all the other modules in the system. With loose coupling, we have less interdependency, we have less coordination and less information flow. Now is the question, which one is better?
Depends.
Depends on?
On like the needs of the software.
The needs of the software, okay.
I'll go with loose coupling.
Okay.
In most cases, because that's the one that's much more maintainable.
Okay, anyone else? So we have one opinion that depends on the context of the software. We have one vote in favor of loose coupling. Anyone else? Anyone has any other opinion? Good. Change. Remember, change. The bloody thing that makes our life as a software engineer a living hell. It could, if you're not careful. Tight coupling means every component of the system depends on a lot of other components of the system. Every class, every method in your software depends on a lot of other methods and classes. What it means is you want to change one of them, you want to change this method, you want to change this class, you want to change this module, and that change has ripple effect. Because you could change this, now you have to change the other module, you have to change the other module, you have to change the other module. So the side effect of the change, the ripple effect, could be enormous. That makes changing your system very, very difficult. Then, we want to design modular systems. We want to have our software entities to be as dependent as possible, starting from the smallest thing in our software, our methods, up to the components that have multiple modules and multiple classes. So it's like, for example, your PC at your home. You want to just go and unplug the CPU and put another powerful CPU there. Don't worry about anything else. Take out the RAM module and insert a faster, more capacity RAM. You want your software to be as modular as possible. In order to be modular, your software needs to have independent components. From the tiniest scale, your methods, all the way up, as much as you can. So at every point of time, when you want to change something, you just take out that particular method or modular component, then replace it with something else, and hopefully then the software works as fine as possible. If your software if you design your software in a tightly coupled manner, then that's not easy. Because in order to take that out, you have to take a lot of things out. So assume that you want to change the CPU, and then that CPU needs another type of, for example, RAM, another type of fan, another type of motherboard, then you have to change everything. That's very more expensive and requires a lot more effort. Although in software you don't see it, so it's way more difficult than changing and upgrading your PC at home. On top of that is reusability. So as software engineers, when you start working, you tend to build these libraries. You design these classes that performs specific tasks, and then every project that you start, you just import your class and keep using that. You don't want to redevelop your classes. Or you reuse the libraries that are built by your team or your company, or off the shelf, you pick it up from the internet. And again, all you want to do is just say import, use. That's it. You don't want to connect any other more plugs. You want your this reusing of your code to be as easy as possible. Otherwise, what's the point of having reusable, basically, libraries? With tightly coupled systems, that would be very difficult. Because in order to use this particular, for example, class, you have to bring in a lot of other classes, and then you have to change your code a lot to work with these particular classes. Everything is just a mess. Everything is connected. So what we want is independent entities, starting from your methods up to the classes. So that's why, for example, in your methods, try to design your methods to be independent as possible. Doesn't require to basically access for the data that are inside another module or inside, for example, another class, rather than just receive all of them as an input argument as much as possible. Now, and in contrast, we have cohesion. The degree to which elements inside the module belong together. So think of a class, a student class. We'll want to model this classroom. Two main entities, a student's lecturer, a student class, lecturer class. What cohesion says is whatever that you put inside the student class and then you close it, it's only about the student. You only put in attributes about the student, methods and properties specifically about the students in the context of that particular application, nothing else. You don't want to put, for example, an operation that is a lecture operation in your student class. That doesn't make sense. You could do it, it's a design, but it's a wrong design. You are designing inconsistent systems. So what basically cohesion says is that the entity that you're focusing, everything that inside that entity are related to each other. They are doing the same work. They are working together towards the same, for example, providing the same functionalities. It's not the same as coupling. You can have a very cohesive student class with very independent modules or independent methods and properties inside the student class. Or you can have a very cohesive class, but then every entity, every method inside the class requires information from other things, which means you have a high cohesion as well as a tight coupling. So what we want, remember this always, remember it by heart. You always want less coupling, maximize independency. And we always want cohesion, maximizing consistency. If you look at this figure, these are your modules. The relationship, the external relationship between your modules are your coupling. So you want to minimize that as much as possible. But then you want all these modules, all these entities inside these modules, such as classes, or if it's a class method that's inside this class, all of them to be very cohesive. They're all focused on the same thing, about the same entity. But then when you zoom in and only look at this module, this relationship becomes co-coupling. And whatever is inside, they become cohesion. So don't forget, less coupling, more cohesion. And that should be your motto when you decide on your classes and your module design, if you're not applying object-oriented principle, how you design your method, how you design your packages, all these different things. Just going to introduce you a few software design smells, and we're going to refer these smells in our analysis as we move forward to the next slide, to the next lesson, and I want you to do this similar analysis in your project as you go forward. So design smells are the odors, the bad odors that come up from your software, and that usually means that you make a mistake somewhere. You either didn't follow good coding practices, or you didn't apply design principles, or your design was somehow flawed. As software engineers, it's your job to identify these smells and fix them. There are so many different smells in software engineering, but we are only going to focus on these seven generic smells in this course. But if you study them and you read papers, there are a lot of more smells that are identified, which you could go and explore as well. Let's go through them one by one. Rigidity. When the system is hard to change, because every change forces many other changes in different parts of the system. What does it indicate? We just talked about it. Tight coupling. That's a direct indication of you have tight coupling. And as such, this is probably one of the most important design smells that you need to cover. A design is rigid when a single change causes a cascade of changes. That's your clue. You're updating one of your methods or one of your classes, and as a result, you end up updating a lot of other things. That means your components, your design is tightly coupled. You need to start introducing independent components into your system. In the next lesson, we're going to talk about some design principles that help you to introduce and add independent components or independent entities. Fragility. You make a change in your software, and then your software breaks in a place that you didn't expect it to break. You touch this module, you touch the accounting module, and then HR component breaks. What does it indicate?
Lack of cohesion.
Coupling. Again, tight coupling. Cohesion definitely feeds to that, but it's again more indication of coupling. Remember, cohesion is internal, coupling is external, and this is an external. You're changing the code here in class A, then the system breaks in class D. It's external. So again, another indication of coupling. So test first development practices would help you a lot in this case to pick up fragile code. In this case, you have pre-designed all the tests, you make the change, then you run all the tests. And if the system fails, then you could pick up basically fragility. But again, this is another indication of a tight coupling system. And if you don't test your system properly, if you don't have a proper testing in place, then your users will pick up the fault, and that's the worst case scenarios. You never want your users to experience fault. You want to capture and fix all the faults yourself before you release the code. Because the moment that the users find faults in your system, if your system breaks on your user, if the app crashes on your end users, it means you're losing users. They're most likely not going to come back to your system if they have other options, and if you lose users, you lose money. Immobility. When the system is hard to disentangle the system into components that can be reused other system. What does it indicate? Tight coupling again. See, that bloody coupling things is the cause of so many different problems. So remember what I talked about. We want modular systems and we want reusable, we design reusable components. So immobility is the opposite. If your system is not reusable, your system is not modular. You can change it easily. You can replace the components. You can reuse the components easily. Viscosity. In software terms and in design smells, what basically viscosity says is doing things in the correct way is harder than doing it the wrong way. So as developers, you are encouraged to proceed with adding more bad code and more bad principles. Because either the software itself is designed so badly that fixing it requires so much effort, and one thing as software engineers we never have is time. We always have a long list of product backlog that we need to go through and address and implement, tick, 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 and our managers want everything to be done yesterday. So that's one thing that we never have time. So then if you see that doing the right thing takes a lot of time and effort, you're just going to do the wrong thing. Just make the software work, don't think about the quality, change, maintainability, all these different things. Or the environment is set up so badly, the technology stack is set up so badly that it doesn't support you to do the right thing.
Could you give an example
Of the environment?
of viscosity?
Well, there's another related order that actually feel that viscosity. So what happens is you start designing the software, initial design. And if you don't have the foundations correctly set up, if you don't have mechanisms in place that makes the software easy to adopt and evolve, then every developer that comes in to add a feature that makes a mess and moves on. The next developer comes in, look at the code and said, what the hell? Well, I can't fix it. I don't have time to go through all this code and fix all of the problems. So, but I still need to basically complete this ticket. So just go and make more mess on that particular module. And eventually, after a while, the module becomes unsustainable. It's not changeable anymore. Then you have two options. Either just use it, as crappy as it is, or delete code from scratch. Either way, a lot of extra costs and a lot of extra efforts. And that's where your software becomes opaque, which relates to the same thing. So remember, you're not always going to be the developer of that particular class, or that particular method, or that particular module. There will be different people moving on, working on your code, or you go work on other people's code. Which means that you need to understand their code, and you need to add to their code. Again, much more difficult than just coding everything yourself from scratch. But you don't have that time to code everything from scratch. If you keep doing that, then your managers will basically call you and say, hey, you're not very productive. No, you still have time. You're not very productive. What's going on? Did I answer your questions? Needless complexity. It's a two-edged sword, basically. So remember, we want to think about change in the future, but sometimes we overdo it. So when we design, for example, a class or a module, we think about that, hey, it's likely that in the future, the client or the manager or the product owner or whoever comes to me and asks to implement that particular feature too. So let me have placeholder available there. So when that request comes in, I can just quickly go and plug it in and everything is done. Which is a good thing in some sense. So you are anticipating change and including that anticipation in your design. But the problem is when you do it, you overdo it. Then you end up with a software that has a lot of unusable parts. And that adds to the complexity to your system. And agile, for example, principles and practices, they usually say, don't do that. Be prepared for change, design for change, but don't implement things that are not needed right now. Needless repetition. The moment that you see duplicate code anywhere in your system, that's a design slow. Because that's the place that you can immediately use abstraction. Put the duplicate code in a separate class and make it available to anyone who wants to use it. Or if it's scattered along in one class, just put them all inside this main code. The moment that you see duplicate code, that's immediate refactoring, and that's a very easy fix, in fact. That's why we have abstraction, encapsulation, and all the object-oriented principles. That affects maintainability of your software and testability of your software significantly. Because if you end up changing that particular code that performs that operation, then you have to keep finding them into your entire solution and keep fix them all one by one, which would be implemented in different extent, which means that you also need to customize them. So you have to need to end up having different versions. And finally, opacity. Is when your code is difficult to read and understand. Everything is everywhere. It's not organized. And that's the result of frequent change on a bad software. Or even you started with a very good foundation, but the other developers who performing those changes don't give a damn about quality. That eventually make your code unmaintainable as unsustainable. So that's where we have clean code concepts, and now pretty much all the development teams, they have review processes to pick up these things and fix them before they are sent to production.
Naming under opacity, that's how you name your variable.
Yes, that's under clean code guidelines. So naming, commenting, and all these things are all under clean code. All right? Questions?